Hi, this is lecture number 7 in discrete optimization on the minimum cost flow problem. That is the most general of all the flow problems that we are considering in this lecture. And to be precise, it's about a specific algorithm, the so-called primal dual algorithm to solve minimum cost flow problems. That is one of the 3 algorithms that are explained in the lecture notes. And the reason to focus on this particular algorithm is because it is matching very well with what I would like to do in the next lecture, because in the next lecture we look at a little bit of polyhedral combinatorics and integer linear programming, and solving minimum cost flow problems kind of is in the same direction. It's a quite general problem already, and the primal dual algorithm also uses a bit of integer programming theory or linear programming theory, which comes handy also later on. Now, but before really defining the minimum cost flow problem, I have to do a little recap of linear programming duality, and in particular complementary slackness, to characterize optimal solutions to linear programs. Okay, so let's just start writing down what a standard linear programming problem looks like. So that is how it looks like. We have a linear objective function. Okay, so x is the variables. We have n variables, so x is a vector of dimension n. And the linear objective function is just a product of c times x for some coefficients cj, right? And we have a set of m linear constraints here. So we have these coefficients in these linear constraints, and here's the right-hand side. So it's larger equal constraints, and we require that the variables x should be non-negative, okay? So that's a standard form of a linear program. And I write primal linear program because we're going to derive the corresponding dual linear programming problem in a minute. But actually, before doing that, I find it more convenient to write down the same problem in matrix notation, which just means we have a constraint matrix A, which is a matrix in dimension m times n, right? I mean, we have one row for each of the linear constraints, which contains the corresponding coefficients in this linear constraint here. So constraint number 1, constraint number 2, and so on. And we have the right-hand sides B, which is just the corresponding right-hand sides of the linear constraints. And therefore, B must be a vector of dimension all of length m. Okay, so the problem reads minimizing c times x subject to these linear constraints ax larger or equal than b, and x should be non-negative. Now, this is a minimization problem. So if I just draw a real line here, we will get solution values c times x for feasible solutions, c times x1, c times x2, and somewhere will be the optimum solution value, c times x star, which I just write down as opt here. And what I'm going to do is I want to find a way to construct lower bound values on this optimum solution value. Okay, so here are all the solution values of feasible solutions to this linear programming problem. Here's the optimum solution. We are interested in computing the lower bounds on this optimum solution value. And this procedure, or this can be done by dualizing the problem. And that works as follows. So if I have a feasible solution for this problem, for this LP, we just consider a non-negative linear combination of all the constraints 1 up to m. Okay, non-negative linear combination. So that means we take a certain fraction of the first inequality, a certain fraction of the second inequality, and so on. So in matrix notation, that would be y times a times x, where this y is a vector of length m, and yi is just how much of the ith inequality I would take. And when I write all this out, so y times a times x, I get this term here, summation over all the m constraints, and each constraint was a summation over all the n variables, so aij times xj. And because of the linear constraints, a x is larger or equal than b, I can replace this bracket here by the value bi, get larger or equal here, and this is just a product of b times y on the right hand side. Okay. Now, why did I do that? Well, I would like to relate this thing here with the original objective function value, which was c times x. Okay. So what we already know is that y times a times x is larger or equal than b times y, just because of the linear feasibility constraints in our LP. And if I also know that y times a can still be upper bounded by the vector c, the objective function vector, then I'm done, because if y times a is smaller or equal than c, okay, then I get the chain of inequalities that c times x is larger or equal than y times a times x, if c is larger or equal than y times a, and that is larger or equal than b times y. So indeed, we have found for the original objective function value, c times x, some lower bound b times y. And under which condition do I have such a valid lower bound? Well, if this vector c is larger or equal than y times a, so I have a constraint on these dual variables y here, right? So these dual variables y have to fulfill these constraints, and when that is true, this chain of inequalities is valid. If I now write down all this explicitly, this looks as follows. So here is again our constraint, namely that c is larger or equal than y times a, or in other words, cj is larger or equal than the product of y times the jth column of the matrix A, okay, for all j going from 1 up to m. And well, then I get, if I write everything out explicitly, I get these chain of inequalities, also known as weak duality, which at the end say that the primal objective function value c times x is lower bounded by this value b times y on the right hand side. And if I write that down in a little bit more convenient form, so once again, here is our primal original linear programming problem. I introduce for each of the constraints a dual variable yi, okay? And I'm just now writing down the corresponding problem that gives me the best possible lower bound that I just constructed in this way. That would be, I maximize the corresponding value of this lower bound that I can get using these yi's. Then this exactly corresponds to the dual linear programming problem. I'm maximizing the linear objective function b times y. That's the lower bound that I compute, subject to the constraints. These were the linear constraints y times a smaller or equal than c, okay? That makes sure that what I compute actually gives me a lower bound on the optimum objective function value. And in order for that to be true, these y values should also be non-negative. So by construction, I have the following situation. All the feasible solutions of the primal problem give me values here, right? That's a minimization problem. All the feasible solutions y of the dual problem give me solution values here. And we just constructed it in such a way that y times b is always smaller or equal than some c times x for some feasible solution x. And by construction, this is true for all feasible solutions y of this dual problem and all feasible solutions x of this primal problem. And just as a side remark, so when I now try to do the same thing again for this linear programming problem, for the dual linear programming problem, namely this is a maximization problem. So if I wish to find the best possible upper bound on the objective function value here, then I will get back the original linear programming problem. So that means the dual of the dual is again the primal problem. So let me summarize that in theorem, or two theorems actually. So that's the duality theorem in linear programming, and we just derived the weak duality theorem, namely for any feasible solution of the primal problem and any feasible solution of the dual problem, we have that the dual objective function value is a lower bound on the primal objective function value, essentially by construction. But even more is true. So not only do I get lower bounds on the objective function value, but if both problems actually admit feasible solutions, then we can also find solutions where equality is achieved. And that's known as the strong duality theorem. So if feasible solution exists for the primal and also for the dual problem, then there exist optimal solutions for both problems, for primal and dual, such that we achieve equality in the above inequality here. And that's the strong duality theorem. Okay, so that means if I repeat my same picture again, I have the optimum solution of the primal problem. I have all the objective function values of the primal problem, which was a minimization problem here. And I have all the objective function values of the dual problems, or of dual solutions here. So here primal, here dual solutions. Then there also exists a primal optimal solution and a dual optimal solution with the same objective function value. So that's the equality here. Now I need one more thing before we can continue with a minimum cost flow problem. And that is, well, the question, under which conditions do I actually get equality here? And that is known as the so-called complementary slackness conditions. So that's actually quite easy. So the conditions are as follows. If I have a feasible solution for the primal and a feasible solution for the dual problem, then actually both are optimum solutions if and only if these complementary slackness conditions hold. And that means the following. So for all the primal variables, 1 up to n, whenever a primal variable is strictly larger than 0, remember they are larger or equal to 0 by definition of the problem. So whenever a primal variable is strictly larger than 0, then the corresponding dual constraint must be fulfilled with equality. And the dual constraint actually said smaller or equal here, but then this must be fulfilled with equality. And likewise, for all the dual variables going from 1 up to m, so whenever such a dual variable is strictly larger than 0, then the corresponding primal constraint must be fulfilled with equality. And remember, the original primal constraints were smaller or equal constraints, larger or equal constraints here. So if these slackness constraints or conditions are fulfilled, we have optimal solutions to both problems, primal and dual. And the proof is quite simple when we just write down the chain of inequalities for weak duality. Okay, so let me do that. So here I repeat the primal problem, that was a minimization problem, the dual problem, the corresponding maximization problem. And when I write down the chain of inequalities for weak duality, we have that the primal objective function value c times x is larger or equal than y times a times x. Why is that true? Just once again, yeah, because c is larger or equal than y times a. And also because I want to have larger or equal here, I have to be careful, because if x would be negative, this was to reverse the sign. So this is true only if x is also non-negative, right? And the same here. For the other inequality in this chain of inequalities for weak duality, this is true because of the primal constraint. So because we have a times x is larger or equal than b, and of the same thing, y is non-negative. And now I'm just asking myself, okay, under which conditions do I get equality on both inequalities here? And that is now quite simple, because I get equality in the first inequality here. So here, well, whenever an x value is equal to 0, I have a 0 here and I have a 0 there, so there is nothing to prove, so they are equal. But for every x that is strictly larger than 0, I should make sure that the corresponding other vector, so c, is equal to y times a. Okay, so let me write that down. So if a value xj is strictly larger than 0, I have to show something, namely then it should better be true that the corresponding value y times a evaluated at the jth position is equal to cj, right? Because for xj equal to 0, there is nothing to prove. Okay, so this is exactly the equality that gives me equality here for all the non-zero x's. And likewise on the other side, if yi is strictly larger than 0, again, when yi is equal to 0, then I have a 0 here and a 0 there, so there is nothing to show. But if it is equal, strictly larger than 0, then it should better be the case that a times x evaluated at the ith position is equal to bi, right? So for yi equal to 0, again, there is nothing to prove, right? So under these two slackness conditions, I indeed get equality everywhere, and that proves this complementary slackness theorem. All right, so that is what we actually need later on as well. So we have a characterization for optimal solutions for both the primal and the dual. We will be primarily looking at the primal, but this optimality proof, comes along with an optimal solution for the dual at the same time. Or in other words, very often in optimization, the optimality proof is just through a dual solution which gives the same value. Okay, so that is a kind of brief recollection of linear programming duality, and then we can move on to the definition of the minimum cost flow problem. And here it is. So in the minimum cost flow problem, we have, just like we had for maximum flow, a directed graph, a flow network, but now we have two parameters per edge. So we have edge capacities, which are now denoted by W, non-negative, and we have edge costs, which are denoted by C for costs, also non-negative. That's a per unit flow cost of the edge. And we have a balance function B, which says that some nodes are production nodes, some nodes are consumption nodes. So that is a required inflow or outflow at each particular node. And the goal now is to compute a feasible flow. So that means essentially balance production and consumption in the network so as to minimize the total cost. So per unit flow, we incur a cost of C for that edge, and we just minimize the total cost that occurs because we are sending flow through the network. Now, a node with a positive balance is called a supply node. That's a node that produces something, it wants to get rid of flow. And a node with a negative balance is a demand node. And this really, if you think about applications, this is exactly what you would think of. There is supply, there is demand in the network, and you have to find a balance between the two at minimum total cost. Now, I didn't yet say what is a feasible flow, but a feasible flow is what you would think it is. So a flow is feasible if it respects the capacity constraints. So the flow value is non-zero and it is at most the upper capacity of the edge, and it has to fulfill the flow balance constraints. So in this case, that means, because we have these balance functions now, that means that the flow out of a node U minus the flow into the node U should be exactly equal to the balance of that particular node. So if it's a supply node where the balance is positive, the outflow is larger than the inflow. If it's a demand node, it's exactly reverse. Note that in contrast to the maximum flow problem, where just for convenience we defined flows to be skew symmetric, we are not doing that here. And in the definition, I say that the flow value along an edge has to be a positive value. So we do not introduce these compulsory backward edges. So there is no skew symmetry here. Flow is feasible if it fulfills these two constraints, and we can have flow only along the arcs that are actually in the network. There is one special case, namely that is when all these balances are equal to 0, and such a minimum cost flow problem or such a flow problem is called a circulation in the network. Okay, so if all the balances are equal to 0, there is no production, there is no consumption, but nevertheless there could be flow in the network. So the flow essentially circulates in the network without going anywhere. And if you think this sounds strange, why isn't that always equal to 0? Of course, this is not necessarily true, right? So here's a little example where if you check at each particular node, the flow into that node is equal to the flow out of that node. So for the source node S, that would be 2 units going out of S, 2 units going into S. If you look at this node here, there is 2 plus 1 going into that node, and there is 3 going out of that node. Same for the target, 3 in, 3 out, and so forth. And even though there is no production or consumption happening in this network, there is a non-zero flow. And if you think about the decomposition of that flow into smaller units, in this case into cycles, that would be a flow of 2 units along this cycle here, and a flow of 3 units along this cycle, and the actual flow from the bottom node to the top node here would be then 1 unit, right? So that would be in this direction 3 minus 2, so there is 1 unit of flow along this arc. And finally, there is one more assumption that we make, and that is this assumption here. It says that, well, first of all the inputs are assumed to be integers, okay? So that is the capacities, the costs, and the balance functions. And we also assume, without loss of generality, that there exists a feasible flow, there exists a feasible solution. That means in particular that the total sum of all the balances should be equal to 0, so total production must be equal to the total consumption, otherwise there can be no feasible solution. And I claim that I can check the existence of a feasible flow, satisfying all the productions and all the consumptions, by just one maximum flow computation in an auxiliary network. And let me show you how. So that indeed this assumption can be made without loss of generality. Okay, so we look at this example here. We have a network on the left-hand side, and there is nodes V and X, which are the supply nodes. They have a positive balance, so this node produces 1 unit, this node produces 4 units, and there's 2 demand nodes, W of -2 and Y of -3. And of course, you already see that the total supply is equal to the total demand, which is 5. Now also remember that we have 2 parameters per edge. So we have a cost parameter, a cost parameter 2, which is here in black. That's the cost of that edge. And we have an upper capacity of 4, which is in red. So that's the upper capacity W. Now the question is, does there exist a feasible flow? So a feasible flow means we have to get rid of these 4 units somehow out of X. We have to get rid of one unit out of V, and 2 units have to arrive here, and 3 units have to arrive here. And the first question that we want to answer is not what is the minimum cost solution of doing that. The first question we want to answer is, does there exist a feasible solution at least? And in order to do that, I use the following trick, which is also a standard trick, say in flow theory. So I introduce instead of having a production node here of 1 unit, I introduce a super source S, okay, super source S, and there will be 1 unit of flow which is allowed to enter into V. Likewise, 1 unit of 4 units of flow are allowed to enter into X. And here on the other side, I will have an outgoing edge on which I can transport these 2 units, which actually have to effectively arrive into W, and I let it flow out of W into some target T. Okay, so this would be the corresponding transformed network. I introduce the source. The original supply of node V is now the capacity of that edge here, and the capacity of the edge ingoing into X would then be 4 correspondingly. Here, this demand of -2 is translated into the capacity 2 here, and so forth. And now what we do is, in this auxiliary network, we compute a maximum flow in this direction from S to T. Okay, and a maximum flow, if it is equal to the capacity of this network cut here, which is exactly the amount that has to arrive in V and X, right? So that is this 1 plus 4. So if the maximum flow is equal to 5 in this network, then we will have found a feasible solution in the original problem as well, right? So the maximum ST flow in the right-hand side network, if that has a value which is equal to 5, so in general that would be the total sum of all the supply nodes, of all the supplies of the supply nodes, right, which here is equal to 5, which anyhow must be equal to the total sum of all the demands. So if that is equal to 5, then we have a feasible solution to the original problem. And of course, this is an if and only if. Indeed, so the flow that happens on the original network, that is exactly the flow that can be translated into the original network, exactly satisfying the required supplies and demands. All right. So indeed, our final assumption here, the existence of a feasible solution, is justified. We can just check that by one maximum flow computation in this auxiliary graph. The next concept that we need, just like we needed it in the maximum flow problem as well, is that of the residual graph. So if we have a network and we have already computed some feasible flow, and we already now know how that can be done, and then we define the residual graph, just like we did before, as the amount of flow that can still be sent on top of the flow that we already have, right? So just like we did it before, if we have an edge from U to V with a cost C and a capacity W, and we have a certain flow value F on that edge, then the remaining capacity on that edge will be just upper capacity minus the flow value, W minus F. And the cost of that flow that I can still send on top of the given flow in that direction has the same cost per unit as it had before. But of course, now we also have the backward arc in the residual graph, which corresponds to lowering the flow value in this direction from U to V. And therefore, the corresponding cost is now minus the cost of sending the flow from U to V. So it will be a negative cost. And the capacity in the backward direction is exactly the amount of flow that I was already sending in the direction from U to V. I think that definition should be clear. It's exactly the same like we did before, with the only difference that now the cost of the backward arc in the residual graph is the negative of the cost of the original arc. Now there is one small peculiarity here, because it could, of course, be that already the original network had an arc from V to U, okay? So that means we might even get parallel arcs, but only 2 of them at most. Let me show you a little example of that. So in the original graph, here in this example, we have this green edge from U to V with a cost of 5, and there is a flow value of 3 in this direction, but also in the original graph, we already had this pink arc in the backward direction with a cost of 2 and say also a flow unit of 1 along this arc. So we're assuming a given flow F in this network. And then that would mean that in the residual graph, we will get a backward arc in this direction, and we will get a backward arc in that direction, which means now in the bottom picture, I have inserted these backward arcs. So the green flow in this direction gives rise to this backward arc. It has a cost of -5 and a capacity of 3 because the original flow was 3. And this flow in this direction of 1 unit gives rise to this pink backward arc in dashed, which, because this was a cost of 2, has a cost of -2 in the opposite direction and a capacity of 1. So such situations can arise in the network. And what will happen, since we are at the end of the day looking for minimum cost flows, all the algorithms will always choose automatically, if there is the choice of 2 arcs, the cheaper ones. Okay, but the total capacity that can be sent, say for example, in the direction from U to V now, that is the residual capacity of the green edge plus the capacity of 1 along this pink backward edge. So that would be a total capacity of 3. And in the opposite direction from V to U, the total capacity would be 1 plus 3, 4, but at different costs. So later on, that will not pose any serious problem. And if you think about sending flow along a path, for example, that path would only use one of those arcs and then typically the cheaper one. So we have defined what a feasible flow is. We have defined the residual graph with respect to a given flow. And now we can move on to look at optimality conditions. So I want to characterize now optimal solutions. So when do we have minimum cost flows? And the first one is very intuitive. The second one is a bit less intuitive, but actually I will be working with the second one. Okay, so here's the first one. So that's the negative cost cycle condition, theorem 7.1 in the lecture notes. So we have a feasible flow is a minimum cost flow if and only if in the residual graph we have no negative cost directed cycle. Intuitively, that makes total sense, because if I have a negative total cost directed cycle with residual capacity at least 1, then I can send at least 1 unit along that cycle. And because it's a total negative cost, I will save money. I will decrease the objective function value. So let's look at the proof of this optimality condition. As I said, the necessity should be obvious, because if I have a negative cost cycle, I could send flow along that. Let's nevertheless look at a small example to see how that works. So here in this example, we have in blue the costs, and here that would be the flow and the capacity. A flow of 1 unit, and the capacity of the edge is also 1. So we have a flow of 1 unit along this path, and we have a flow of 1 unit along that path. And if you look at it, you already see that I'm using here an expensive edge of cost 3, whereas there is a cheaper alternative. I can also still send 1 unit of flow using a total cost of 1 plus 1, that is 2. So certainly this is not a minimum cost flow, and I would like to redirect this flow unit along these edges, and that's exactly sending the flow along a negative cost cycle, which is actually this cycle here, which has a total cost. Well, what is the total cost? That would be 1 plus 1 plus -3, because since we have a flow in that direction, in the residual arc, we have an arc in the opposite direction of cost -3. So here is the corresponding residual graph, just to convince you. And here we have this negative cost cycle, which we can use and decrease the total cost of the flow without changing any of the balances at any of the nodes by 1 unit. Okay, So as I said, necessity is indeed obvious, and this is just once again an example to see how that works. So indeed, we just use this negative cost cycle to reduce the costs if they are present. By the way, this already gives rise to an algorithm, but I will come back to that a little bit later. Now, the condition that a network or the residual graph has no negative cost cycle is also a sufficient condition. And to that end, we have to give a proof as well. So given is a flow, and let's assume there is no negative cost cycle in the corresponding residual graph anymore. And I consider an arbitrary other flow f prime. And we show that the flow f, which is the flow without a negative cost cycle in the residual graph, is cheaper than this arbitrary other flow f prime. And the first step in that proof is to look at this difference of the flows. You probably remember the same argument from maximum flows. So we consider the difference flow f prime minus f. So flows are just vectors of length m. We can subtract them from each other. And I claim that this is a feasible flow in the residual graph of flow f. It says here non-trivial but straightforward. Just check the constraints. I think it's instructive to do it nevertheless. So let's do that. So the claim is this difference flow f prime minus f is feasible in the residual network for f, for GF, the residual graph. So this is the situation. We have some flow value from u to v, and the cost is c, and the residual capacity is original capacity minus flow value, and therefore in the backward direction, that is now the arc that corresponds to this forward arc here, we have a negative cost value c of e and a capacity equal to the flow value. Now I pick any edge in the network, and there is two cases. Either this difference flow is non-negative or this difference flow is negative. So let's look at these two cases separately. First of all, let's assume that this difference flow is non-negative. Well, then we have that, if I just write down this difference flow again, f prime minus f, because f prime was a feasible flow, the flow value is bounded by the upper capacity of the corresponding edge. So this would be at most w of e minus f of e, which is exactly the residual capacity in the residual network with respect to f. So here we are actually done. Okay, so that's fine. If on the other hand, the flow value was a negative, the difference flow is a negative value, that can only happen if we have a positive flow, if this is a positive number here, because remember that the flow values are non-negative. So that means there is a positive flow on the edge E, and that means if we have a positive flow on the edge E, I guess the edge E goes from U to V, then we have the residual arc in the backward direction in the residual graph. So a negative flow in the direction of from U to V translates to a positive flow in the opposite direction. So we have a positive flow in the opposite direction on the arc from V to U. But now we get that the flow value in that direction, so f of E minus f prime of E, because f prime was a feasible flow, which is non-negative, this is at most f of E, which again is exactly the residual capacity of the corresponding backward arc in the residual graph, right? So there's the residual capacity. So also here we are fine, and we are respecting the residual capacity, and that's it. So indeed, this difference flow is feasible in the corresponding residual graph for f. Next, claim is that this difference flow must be a circulation. So that means all the flow balances of this difference flow must be equal to 0, which is clear because if we look at any particular node, then say with an excess of 5, then this flow satisfies this excess of 5, and so does this one, and the difference of 5 minus 5 is equal to 0. So this difference flow is a circulation in the network, and I can actually decompose any circulation in a network into the sum of at most m cycle flows, so flows on simple cycles. Okay, and m is the number of edges in the graph. That follows by the flow decomposition in the lecture notes lemma 7.1, but also here I at least would like to remind you how I can see that. So the lemma says that for any circulation, I can express the corresponding flow, so F is a circulation, that's the same F here, as the sum of K cycle flows. So Ci is a simple cycle and Gi is a flow value along that cycle, where K, or the number of these cycles, is at most M, the number of edges. And the idea is quite simple. So first of all, you repeat the following simple procedure. First of all, try to find the first of such simple cycles with a positive flow value. Okay. How could I find such cycles? I mean, I don't have to give an algorithm here, but the existence is sufficient. Nevertheless, I just pick an edge with a non-zero flow. This, because it's a circulation, the flow must get there somehow, and I just continue backwards along the flow values. And because the graph is finite, I mean, I start here, and because the graph is finite, I must find a cycle at some point in time. So this is the first cycle that I find. I look at the minimum flow value along all these edges. So it's all non-zero. And that would be the corresponding minimum flow along that cycle. And G of C is now the cycle flow of that amount R along that cycle. And now I just subtract this cycle flow from F. I take F minus G. And that means because I took the minimum flow value along that cycle, at least one of the edges will have zero flow afterwards. So after I've done that, at most m times, all the edges will have a zero flow. So that's already the proof of this flow decomposition lemma for circulations. Okay, so we have shown that this difference flow F prime minus F is the sum of at most m cycle flows. And now comes the final step. Each of these flows along cycles must have non-negative costs. Why is that? Well, because we assume there exists no negative cost cycle in the residual network anymore. And these cycle flows are all feasible flows in this residual network. So none of them can have negative costs. That's our assumption. And now we can just express the cost of this arbitrary flow F prime. This is just vectors, right? That's the cost of F prime minus F plus F. So I just add this 0 here. Everything is linear, so that's the cost of the difference flows F prime minus F plus the cost of F. And we just argued that this difference flow is the sum of at most m cycle flows. None of them has negative costs. So this thing here is non-negative. And therefore, this is at least as large as the cost of F. And that's exactly what we wanted to prove, because we wanted to show that F, our flow without a negative cost cycle in the residual graph, is better, cheaper than this arbitrary other flow F prime. And that's the end of the proof. So that is the first and very intuitive characterization of minimum cost flows, namely by means of non-existence of negative cost directed cycles in the residual graph. And in order to motivate the other, maybe a bit less intuitive optimality condition, I want you to think back of linear programs. So what did I do for linear programs in the first couple of slides? So there we had an optimality certificate by means of existence of a dual solution, such that primal and dual achieve the same objective function value. And that's exactly what is happening in this other condition. So question is, can we come up with a kind of dual characterization of optimal flows, minimum cost flows? So existence of dual variables with certain properties, namely complementary slackness. And that's exactly what we do. And in order to formulate that, we say, okay, a flow is a minimum cost flow if and only if there exist node labels. I will refer to them as node potentials as well, pi of u for all the nodes in the graph, so that the so-called reduced cost optimality condition is fulfilled. Later on, we will show that this condition here is equivalent or is exactly the same as the complementary slackness condition. But for the moment, I just give the definition. So the reduced costs of an edge from U to V, that's the original cost minus the potential difference. So we have these dual variables, potentials for all of the nodes. So along an edge, we have a potential difference, pi of V minus pi of U, and that is added to the original costs. So that is the reduced cost along an edge. And we define that for all the edges in the residual graph. So just again a little picture in order to illustrate that. So we have an arbitrary edge in the residual graph. It has a certain cost C, and we have a potential for the two endpoints, the head and the tail. And the reduced costs along that edge, that is just the original cost plus the potential difference. So that is P of V minus P of U. And I think I didn't even say what the statement of the theorem is. We have a minimum cost flow if and only if there exists such node potentials pi such that the reduced costs, so defined, are non-negative for all the edges in the residual graph. Now notice that this is a optimality condition by means of a new set of variables, namely variables for all the nodes of the graph, whereas the primal solutions, which we are interested in, that is flow values on all the edges of the graph. So indeed, it's maybe a bit less intuitive, but nevertheless, it's quite simple to prove that this is a characterization of optimal solutions. So let's do that. So it's a necessary condition. So that means when we have an optimal minimum cost flow, then we already know by our primal characterization that I proved earlier that the corresponding residual graph has no negative cost cycles. That means in this residual graph, we can compute shortest paths with respect to the costs, because there is no negative cost cycle that is well defined. So let's do that. We compute shortest, I call them cheapest paths here, from the source node to all the other nodes U. And the shortest path lengths or cheapest path lengths are denoted by D of U. And they exist because our assumption is that there is no negative cost cycle. So cheapest here really means with respect to the original cost function. All right. So once we have computed that, we just define the potential of a node U as just a negative of these cheapest path lengths. Okay, so P of U is defined as minus D of U. D is the distance from the source to U. Because this is shortest path lengths, they fulfill the triangle inequality. Right, so if I have an edge from U to V, then I know that the distance label of V is at most the distance to U plus the length of the corresponding arc. So that is the triangle inequality, and it's repeated up here. And now I just have to rearrange terms. Now I see if I rearrange this triangle inequality, I get that C of U plus D of U minus D of V is non-negative. And if I write that down, that is exactly the condition that C of the cost of the arc plus the potential of V, because the potentials were the negative of these distances, so plus the potential of V minus the potential of U is non-negative. And that was exactly the definition of these reduced costs of the arcs. Okay, so once again, if I have an optimal flow, I know the residual graph has no negative cost directed cycle anymore. And then I can define these node potentials pi in such a way that these reduced costs are actually negative for all the edges in the residual graph. So it's indeed a necessary condition. In order to show that it's also a sufficient condition, I consider an arbitrary flow and a set of node labels pi along with it that fulfill this reduced cost condition. So the reduced costs are non-negative in the residual graph. And now I consider an arbitrary cycle in the residual graph, and I'm actually going to argue that the cost of such a cycle must be non-negative. And then we can use our previous characterization, and again we have that we have a minimum cost flow. Okay, so considering an arbitrary cycle in the residual graph GF, what are the costs of that cycle? Well, that's just the sum of the costs along the edges of the cycle. But now, since this is a cycle, I can replace the cost by the reduced costs, because this is a sum along a cycle, so all these terms will cancel each other out in total, just because we are summing over a cycle. And therefore, now, next I know that all these reduced costs are non-negative, right? So first of all, this is equal to the sum along the cycle of all the reduced cost coefficients. They are all non-negative, so therefore the whole sum is non-negative. And that means that the total cost of this cycle in terms of the original cost is also non-negative. So that means for an arbitrary cycle in the residual graph, I know that the total costs along that cycle must be non-negative, and that is our previous characterization of minimum cost flows. So as you see, the proof of this a little bit less intuitive characterization is even simpler as the other one. Sorry, simpler than the other one. Okay, so by now we have two characterizations of minimum cost flows, one by negative cost directed cycles in the residual graph, and the other one by non-negative reduced costs in the corresponding residual graph. And based on these two theorems, you can come up with different algorithms for which then, using these theorems, you can prove optimality of the corresponding solutions. And before I do that, let me just make one more assumption. So it's without loss of generality that we can restrict to the situation where all the node balances are equal to 0. And we want to send a certain flow value, denoted VAL here, from the source node to a target node. Remember the previous transformation where we introduced a super source and a supersync T in order to verify if there exists a feasible solution at all. So assume we have computed such a feasible solution in the first place that sends a certain flow value from S to T, but it's probably not cost optimal, right? So that's the problem that we can look at without loss of generality, and that's what we are doing. Now, the first class of algorithms to compute minimum cost flows would be exactly to start out like I just described. I start with a feasible flow in the beginning, sending this certain value VAL from S to T. So I start feasibly and I maintain feasibility throughout the algorithm, and I work towards optimality by sending cycle flows along cycles with total negative costs, right? So that's negative cycle canceling algorithms. And there is even versions of that, namely the minimum mean cycle algorithm that run in time, which is polynomial in the size of the network. The other class of algorithms, and that's the one that I'm going to explain in the rest of this lecture, that's a primal dual type of algorithm. So here the optimality proof relies on non-existence of negative cost cycles at the end. Here the optimality proof will rely on these the non-negativity of the reduced costs at the end. So the idea, the fundamental idea is different here. We start out with a zero flow. That's actually an infeasible flow. But it's a flow, I mean, for the given flow value 0, this is the minimum cost flow as well, right? Because the cost is 0 too. So we start out with an optimal solution for the current flow value. And throughout this algorithm, we will maintain optimality. And we will work towards feasibility by sending more flow from S to T until we have achieved the right value. So in contrast to maintaining feasibility and working towards optimality, we maintain optimality throughout and work towards feasibility. And for the sake of completeness, we might refer to such flows which violate some of the balance constraints. We might refer to such flows as pseudo flows, even though I'm not really doing much with that word. But that would be flows which fulfill all the capacity constraints, but still might violate some of the supply and demand constraints. So that will be the algorithmic idea of the primal dual algorithm. And before I do that, I still would like to convince you that this reduced cost optimality condition is exactly the complementary slackness condition that I just explained in the beginning for linear programming. And in order to do that, of course, we need to formulate the minimum cost flow problem as a linear programming problem. And to get there, we need the so-called node arc incidence matrix A. So that's just the incidence matrix of nodes with the directed edges in the following form. So if I have an edge going from U to V, then in this matrix, I have entries A, U, E, which are equal to +1 when the node U appears at the tail of E, -1 when the node U appears at the head of U, and 0 otherwise. Okay, so let's look at a little example down here. If we have now the constraints, the flow balance constraints will just read as A times F equal to B. B is the node balances, F is the flow vector, and A is this node arc incidence matrix. Okay, so if we have an edge from U to V, remember that means there is a +1 here at U because U is the tail of that edge, and a -1 for V here because V is the head of that edge. And there is another edge from U to W, +1 here at U, -1 here at W. Okay. And if I look at one particular row of this multiplication here, A times F, what do I get? Well, then I go through such a row here, and that means I will have a +1 for all the outgoing edges for a node U. So if I look at A times F for a particular node U, so that would be this row here, then I will have a +1 for all the outgoing edges of U, and I will have a -1 for all the ingoing edges of U, and that exactly collects the whole outflow out of U minus the total inflow into U, and that should be equal to the flow balance constraint. Right, and in this way we can just formulate the whole problem. So if A is the node arc incidence matrix, C was the vector of the costs of the arcs, W is the vector of the capacities, and B is the node balances, which in total have to sum up to 0, then the minimum cost flow problem is this linear programming problem. So we minimize C times F, total cost of the flow, subject to the constraints that the flow balances are fulfilled, and I just convinced you that that means A times F is equal to B. And then we have the capacity constraints, so the vector F should be smaller or equal than W, and I can just write that as the unit matrix E here times F, or minus the unit matrix E times F is larger or equal than minus the capacities, because I would like to have larger or equal constraints, and the flow value should be non-negative. And remember that we are considering the special case here that the flow balances are all 0 except at S and T, where there are plus some value and minus some value respectively. And now I have a formulation of a linear programming problem, and I can just write down the corresponding dual. And let me do that. I'll do that on the next slide. And here I express the primal LP again in the standard form in which we would write it down usually. So linear cost function, flow balance constraints here for all the nodes of the graph. Costs or flows should respect the capacity constraints W, and the flows should be non-negative. Now, in order to set up the corresponding dual, we will have two sorts of dual variables, namely one for each of the constraints. And we have these equality constraints here, right? And for these equality constraints, we will have a variable pi of u for all the nodes of the graph. And we have these capacity constraints here, that's also inequalities. And we will have one dual variable also for each of those guys. So I denote them by alpha. Now, how does the dual for this LP look like? So what are the dual constraints specifically? To that end, look again at this picture. So this up here is what we already had on the previous slide. So we know that already. So that's just the flow balance constraints formulated in this matrix form with the node arc incidence matrix. Now here again, I have written down the minimum cost flow problem. So we have two sorts of constraints. We have A times F is equal to B, and we have minus identity matrix times F is smaller or equal. I think it should be a larger. Indeed. So minus identity matrix times F larger or equal than minus W. And we have the corresponding dual variables pi and alpha here. Now I just write down the corresponding dual problem mechanically. So what was the dual problem? So that was the dual variables times the corresponding right-hand side. So that will be pi times b plus alpha times minus w. Okay, so that's what we have as objective function in the dual. So that is maximize pi times b minus alpha times w. And what are the dual constraints? Well, that was dual variables times constraint matrix is at most a cost function vector here. So I write down what that is. So here's the dual variables times the constraint matrix is at most C. Okay. So I do have a dual variable, a dual constraint for each of the edges in the graph. Okay, and how does this dual constraint look like? Well, that would be one such constraint would be pi alpha times one of the columns of this matrix here is at most the corresponding value Ci, right? So let's do that. Write that down. And then I get for all the edges UV of the graph, I'm collecting, if I look at such a column, I'm collecting pi of u minus pi of v. Okay, pi of u minus pi of v. And then I also have the identity matrix appearing here. So there is also an identity matrix which comes down here. And that means in this dual constraint, I'm also collecting the corresponding alpha value. So that means what I get is minus alpha from u to v. And that is at most the corresponding right-hand side, which is, so that is at most c of uv. So the cost for the edge from u to v. And if I now just rewrite this, because here you will see the reduced costs popping up. So that exactly means minus alpha uv is at most the corresponding reduced cost on the edge from u to v. Okay, so we have found or formulated our dual problem explicitly, and these are exactly the constraints that I had written down earlier. Okay, so let me now just again go through the steps simplifying these dual constraints here. Oh yeah, by the way, I forgot to mention one thing. So in the dual, the alphas are required to be non-negative. So the alphas were the variables that belong to these inequalities here. Actually, the pi's are unrestricted in sign because they correspond to equality constraints, and the dual variables for equality constraints are always unrestricted in sign. That's quite easy to see if you exactly write down the standard form and you split up positive part and negative part, but I'm not going to do that. Okay, so here we see again the corresponding dual. The alphas are non-negative, the variables pi are unrestricted in sign, and that's the dual constraints. And the objective function is the sum of b times pi minus w times alpha. All right, so let's now just simplify the definition of the dual, remembering that these were the reduced costs that we defined earlier. Then we will recognize that these reduced costs actually show up in these constraints. That is what I already did on the previous slide. So let's just do that. And we will see that the dual constraint becomes minus alpha along an edge E is at most the corresponding reduced cost of that edge E. And for the future, it's even more convenient to write it as alpha is at least minus the reduced cost along that edge. Now, when I stare at this dual long enough, I can make a few observations. And the first one is this. So we have a maximization problem. And so we would like to have all this together as large as possible. So in other words, this sum should be as small as possible. And the W's were the capacities, they are non-negative, and the alphas are constrained to be non-negative too. So that means we would like to make the alphas as small as possible in an optimal solution. And the only thing that hinders us to make them all equal to 0 is these dual constraints here, right? So let me say that again. So since this is all non-negative, we would like to make the alphas as small as possible. And that exactly means that given values for pi, which define these reduced costs here, right, or the negative of the reduced costs, I will set the alpha values as small as possible. And that is actually either equal to 0 if possible, and if the reduced costs are negative, then because of these constraints here, I have to set the alpha values a little bit larger, namely to something strictly positive. So that is to say that in this dual problem here, only the pi's are the interesting variables because the alphas are kind of dependent on the pi's, and once the pi's have been determined, and remember the pi's define the reduced costs here, then I know what the alphas should be. Okay, so only these variables pi are the relevant variables. Okay, so now that we have written down both the primal and the dual LP, we have understood a little bit how this LP or the mechanics of this dual LP works, we can try to formulate the complementary slackness conditions, because that is eventually what I need in order to characterize optimal solutions. So remember, primal complementary slackness said that when the primal variable is strictly positive, the corresponding dual variable should be fulfilled with equality. Okay, so let's write that down. Primal complementary slackness. When the primal variable is strictly positive, the corresponding dual constraint is fulfilled with equality. But this equality here can only be fulfilled if the corresponding reduced cost variable is non-positive, right? Because if this is positive, then this would be something strictly negative, but the alphas are non-negative. Okay, so this can therefore be reformulated. If the primal variable is strictly positive, then as a consequence, the corresponding reduced cost coefficient should be non-positive. And then the alpha can be exactly set to that value, and we can fulfill that constraint. So let's say that again, if the flow is strictly positive, the corresponding reduced cost coefficient is at most 0, but in other words, that is to say that if this is strictly larger than 0, then the flow value must be equal to 0. Okay, so if the reduced cost is strictly positive, then the flow value must be equal to 0. And that's the way we actually need it. Okay, so that was primal complementary slackness. So let's look at dual complementary slackness. And we need to do this complementary slackness stuff for the dual constraints only, for the dual variables only for alpha, because for the pi's, the corresponding constraint were equality constraints. So these are equality constraints already, right? So therefore, there is no complementary slackness conditions for those. But if an alpha, if a dual variable alpha is strictly larger than 0, then the corresponding primal constraint, that was the capacity constraint, is fulfilled with equality. So that means the flow value is equal to the upper bound. But once again, when can alpha be strictly positive? Well, remember the definition of alpha, that was this, right? So these alphas are the derived variables which depend solely on the reduced costs. And alpha can be strictly larger than 0 only if this is strictly larger than 0. And that means that happens only if the reduced cost is strictly smaller than 0. So that means if the reduced cost is smaller than 0, then the flow value must be at the upper capacity limit. So we have two sorts of constraints now, which kind of look the same, at least syntactically. If the reduced cost is strictly positive, the flow value is equal to 0. If the reduced cost is strictly negative, the flow value should be equal to the upper capacity limit. And that means the flow value can be something in between only if the reduced cost is equal to 0. So let's summarize that. The flow is equal to the upper and lower bound constraints unless the reduced cost coefficient is equal to 0. And remember that we are talking about minimum cost flow solutions, optimal solutions here. So that is the complementary slackness condition. So let's summarize all of that. Okay, so that's the theorem again, complementary slackness optimality condition. I just summarize what I already said. Feasible flow is a minimum cost flow if and only if in the corresponding LP formulation it fulfills complementary slackness. And that means if there exist dual values pi for the nodes, such that for all edges of the graph, if the reduced cost coefficient is strictly larger than 0, the flow value is equal to 0. If the reduced cost coefficient is smaller than 0, the flow value is equal to the upper capacity. And now, surprise, surprise, this should, of course, be equivalent with our other characterization, which we called reduced cost optimality condition. And that said that the reduced cost should be non-negative in the residual graph. So let's have a look why this is indeed, as a sanity check, 1 and 2 together is indeed equivalent with 3. Okay, so as a sanity check, as I announced, this is 1 and 2 together. It said something about, well, the reduced cost being strictly positive or strictly negative, then the flow values must be 0 or at the upper capacity limit. And that should be equivalent with our reduced cost optimality condition, saying that the reduced cost coefficients are non-negative for all edges in the residual graph. Okay, so let's first go in this direction. So 1 and 2 are fulfilled, and we have to show 3. So let us pick a forward edge in the residual graph from U to V. And then we know this edge is a forward edge in the residual graph. That means the flow value is below the upper capacity limit. And that's the reason why this forward edge still exists in the residual graph. But if the flow value is smaller than the upper capacity limit, that means we cannot be sitting in this case here, right? So it cannot be the case that the corresponding reduced cost is smaller than 0, because then the flow value should be equal to the upper capacity limit, and it's not. So therefore, the reduced cost must be non-negative. Okay, so we just know from 2, because the flow value is not at the upper capacity limit, that the reduced cost along that edge must be non-negative, and we are done. Next, let's consider a backward edge in the residual graph. So why does a backward edge exist in the residual graph? Because we are sending flow in the forward direction. So if the edge VU exists, we are sending flow from U to V a positive amount. Now, since we are sending flow, a positive amount, strictly positive amount of flow, we cannot be sitting in this situation here. So it's non-zero. So that means the corresponding reduced cost is non-positive. So let me write that down. So by 1, we know that the corresponding reduced cost coefficient from U to V is non-positive. But I know what the reduced cost coefficient is on the opposite arc, on the arc in the other direction. So if this one is non-positive, then the one in the other direction is the negative of that, and that is non-negative. Okay, so that means the reduced cost coefficient from V to U, which is equal to minus the reduced cost from U to V, that one is therefore non-negative. And again, we are in shape. So let's look into the other direction. So if 3 holds, we should get 1 and 2. So we pick an arbitrary edge in the graph, and we have to show that these two conditions are fulfilled. Let's do that. So if the reduced cost along an edge UV is smaller than 0, non-positive, because all the reduced costs are non-negative in the residual graph, we know that this edge cannot appear in the residual graph. So let's write that down. So the edge UV is not in the residual graph GF. Why is it not in this residual graph? Well, that is because the flow value is at the upper capacity limit. That's the only way how an edge can disappear from the residual graph. So that means the flow value from U to V is equal to the capacity from U to V, and that's exactly what we wanted to show. Right? So if the reduced cost is smaller than 0, the flow is equal to the upper capacity value. Now, finally, if the reduced cost is strictly positive on an edge UV, then I know it's strictly negative in the opposite direction. So the reduced cost from V to U is strictly negative, which again means that the edge in the opposite direction cannot be part in the residual graph, because in the residual graph they are all non-negative. So we get the conclusion that the edge from V to U is not in the residual graph GF. But if the edge from V to U is not in the residual graph, on the edge from U to V, we cannot have any flow value, right? So that means the flow value from U to V, the forward direction, must be equal to 0, because otherwise the corresponding edge would be part of the residual graph. And that again is the condition that we wanted to show. Okay, so we are done with our sanity check, and indeed we have shown that the sanity check was okay. So the characterization, the complementary slackness characterization of optimum solutions minimum cost flow is equivalent with our earlier reduced cost optimality condition. Okay, so in that sense, it's fair to say that this reduced cost optimality condition is exactly a complementary slackness condition when I consider minimum cost flows as linear programs. So having all this set up, we can actually formulate quite easily the primal dual algorithm. Okay, so in order to formulate this primal dual algorithm, as a matter of fact, we will make use of both optimality conditions, both characterizations of minimum cost flows. So eventually, in order to prove correctness of the algorithm or optimality of the flow that we have in each iteration, we will make use of this slackness optimality condition, but along the way we will also use the reduced cost optimality condition. So we actually need both characterizations in order to formulate and understand the algorithm. Okay, so let me give you a high-level idea of how the algorithm works. We start out with a zero flow and zero potentials. Remember that we start with a flow that does not yet fulfill the required value of the flow, and that is certainly true for a flow of value 0. But this is an optimal primal dual pair. So zero flow and zero potentials fulfill complementary slackness conditions. So we start out with an optimal solution for the given flow value, which is equal to 0. Now let's assume we have in some iteration computed some flow f, which is an optimal flow for the given flow value, and we have the corresponding node potentials pi. So that's an optimal primal dual pair. And what we do is we want to augment this flow and still remain optimal for the new flow value. Okay, so that's what we do. And how do we do that? Well, the first step is to compute shortest paths in the residual graph. So we compute shortest path in the residual graph, GF, where shortest should be read or understood as cheapest, because we use as lengths of the edges the residual costs. Okay, notice that the residual costs in the residual graph, and here we need the second characterization, they are all non-negative. Because we started out with an optimal primal dual pair for the current flow value, we know that in the residual graph, all the reduced costs are non-negative. So we can compute a shortest path tree in this residual graph for these costs. Now, what is this, or what does this shortest path tree represent? You should really think of the ST paths in this shortest path tree as the remaining flow augmentation options, and then the length or the total cost of such a path really corresponds to the cost that it would send to send 1 unit of flow along such a path. Now what we want to do is we want to augment the flow while remaining optimal. And how do we do that? So first of all, we redefine the node potentials. So the new node potentials pi prime are the old ones minus these shortest path distances. Okay, so that will actually allow me to send more flow from S to T, and you will see in a minute how that works. So by definition, that will have as a consequence that the new reduced costs are actually equal to 0 along the whole shortest path tree. And I think it makes sense to quickly verify that this is true as another kind of sanity check. Okay, so let's see. So the new reduced cost should be 0 along the shortest path tree. Now this here is an edge on the shortest path tree that was computed using the old reduced cost C pi, right? So how did we define the new node potentials? That was the old node potentials minus the distances. And because this is an edge on the shortest path tree or on a shortest ST path, I know that the distance to reach V is actually the distance to reach U plus the length of this arc, right? We got here along the shortest path along this edge. So the distance is the distance of that one plus the length of the edge. That's the definition of shortest paths. Now, what is the definition of the new reduced cost coefficient? That is the cost of the edge plus the potential difference. Okay, and now we just plug in the values of these new node potentials pi prime. So let us do that. So that is just the cost from U to V minus, and what was pi prime? Well, that was actually pi of U minus d of U, right? Plus pi of V minus d of V. Now I just have to reorder this summation here. So this is the cost from U to V minus pi of U plus pi of V. So that is one part, minus d of v plus, oh no, sorry, minus d of u. And now this first part here is just the old reduced costs, so c pi from u to v. And what is this? Well, let us remember that we had this equation because this edge was on a shortest st path, right? So that means the reduced cost, the old reduced cost, c pi, is equal to d of v minus d of u. And that's exactly what we have here as well. So that's also the old reduced cost from u to v, and therefore the whole thing is indeed equal to 0. So that was exactly what we wanted and how we wanted to define it. Now we have convinced ourselves that indeed the new reduced costs are equal to 0 on the shortest path tree, so on all shortest ST paths that we still have in the residual graph. And that is a nice thing, because remember the complementary slackness optimality conditions. It said something about edges which have strictly positive or strictly negative reduced costs, but we could do anything on edges which have a 0 reduced cost. So that means we can now actually send flow along these shortest paths here, because they all have reduced costs equal to 0. So when we send additional flow along these ST paths here, we still maintain optimality. And that's exactly what we are doing. So we augment the flow by computing a maximum flow in the residual graph, but not in the whole residual graph, only in the residual graph that contains all the edges which have a 0 reduced cost coefficient. Okay, so we know that this graph here contains all the shortest paths from the shortest path tree that we previously computed. And that means that the flow value changes only on edges which currently have a 0 reduced cost. And that means that we obtain a new flow which still fulfills the optimality condition. So the complementary slackness condition will be still fulfilled, because this condition only said something about edges which have strictly positive or strictly negative reduced costs. Okay, so let me summarize this in this pseudocode description of the whole algorithm. We start out with a 0 flow with currently a value of 0. In the beginning, the residual network is just the graph itself, and all the node potentials are equal to 0. And we go through this while loop as long as we do not fulfill the required total flow, right? So as long as the value of the flow is still smaller than what we want it to be. And in each such iteration, we first compute the shortest path distances in the residual graph, and we get as edge lengths the residual costs of the edges. We update the node potential, so this would be the pi prime here, right? By subtracting these shortest or cheapest path distances. We define the network, the subnetwork, consisting of only the edges which now have 0 reduced costs. We compute a maximum ST flow in this subnetwork. So this G0, little g0, is a maximum flow. So here we need a maximum flow algorithm in order to be able to do that in this subgraph. And we just add this flow to the current flow F. Okay. And afterwards, we have to update the residual graph, the current value that we have, and also the reduced costs. And this works because when we add this flow, or when we compute this maximum flow in the subnetwork, only consisting of edges with 0 reduced costs, in some sense we are not touching the optimality conditions. So the new flow will still be optimal because it will still fulfill the complementary slackness optimality condition. So let us look at a little example before we go over the correctness proof. So here we have a kind of trivial graph. You already see that. So the required flow value should be equal to 2. In red, we have the capacities, and in black, we have the corresponding costs along the edges, okay? And you already see that there is 2 units of flow that go out of S. 1 unit goes along this path, and another unit has to go along this path. But let's see how the algorithm performs on this example. So the first thing to do is to compute the shortest path distances with respect to current reduced cost coefficients, and that is these reduced cost coefficients in the graph. So therefore, the distance from S to U is 1, the distance from S to T is 2, the distance from S to V is 3, and hence remember that we subtract the shortest or cheapest path options from the current node potentials, and we started out with 0 node potentials. So that means U will get a node potential of -1, T will get a potential of -2, and V will get a potential of -3. Now you already see also here the new reduced cost coefficients and exactly the corresponding shortest path tree consisting of the edges which have a 0 reduced cost. Okay, so that will be our network in which we compute a maximum flow. And here I just copied the corresponding residual capacities along the edges. So we have to compute a maximum ST flow in this subnetwork, which in this case is just a flow along this path, and the capacity would be equal to 1. So that's what we do. We send the flow value from S to T of value 1. And that essentially finishes this iteration, and we have to recompute everything. So we update the residual graph. So now we get, for example, this residual edge here. This edge has been turned around in the residual graph. It's now pointing in the other direction because the edge from U to T is saturated. And what you can also see in this new residual graph, for instance, is that all the reduced costs along all the existing edges, all these are non-negative, and that is our optimality proof, the reduced cost optimality condition. On the next iteration, we would again compute shortest paths from S to T. That would be a distance of 0 here, a distance of 0 here, and the distance to get to T would be equal to 1 because of this reduced cost coefficient equal to 1 here, and therefore there will be an update in the corresponding node potential for the node T. So this will be -2 minus the shortest path length, which is 1, so this will become -3. Now again, we will have updated reduced cost coefficients, and this, by definition, this reduced cost coefficient will turn out to be 0, and you already recognize that there will now be again a path from S to T in the residual graph with 0 reduced costs. And that is what is happening. So here is again the new updated residual graph with all the edges with 0 reduced costs, and there is again an ST path or an ST flow that we can compute, so we can send this one additional unit along this path, and that is what we do. So we send 1 unit of flow and realize that the flow value is now equal to T. So let's additionally look at the new residual graph that we obtain after we have sent the 1 unit of flow, that is this one. So this edge is now turned in the other direction. So is this one, and so is this one, because all these edges are now saturated in the other direction. So looking at the reduced costs, we again observe that the reduced costs, the new reduced costs in this residual graph are all non-negative, which is one of our optimality conditions. Thinking about our complementary slackness optimality condition, we could, for example, look at this edge here. It has a strictly positive reduced cost coefficient, and that means that the flow value must be equal to 0, which is indeed true because we are actually sending 1 unit of flow in this direction, and 0 units in that direction. In the opposite direction, in this direction, for instance, the corresponding reduced cost coefficient would be -1, so a strictly negative reduced cost coefficient, and that means that the flow should be at the upper capacity, which is true because we are sending 1 unit of flow in this direction. So just to verify some of the optimality conditions here. Okay, so much for this example. So let us have a look at the correctness of the algorithm. So let us first convince ourselves that the algorithm really terminates, but that is simple. Because as long as the flow value is not what it should be, we will have an augmenting path in the residual graph. Okay, and that means by definition of the subnetwork consisting of only the 0 reduced cost edges after we have updated the node potentials, that will have a flow value of at least 1. So in each iteration, we are increasing the flow value by at least 1, and therefore we will terminate after a finite number of iterations. How do we show correctness? And this we do in the following way. So we started an iteration with the assumption, it's an inductive proof on the number of iterations. Obviously, we started by assuming f and pi fulfill complementary slackness for the given current flow value. Okay. So, and we have updated the node potentials to be pi prime, subtracting these cheapest path lengths. And what I'm going to show is that with this flow and the new node potentials, I still fulfill complementary slackness. So for the current flow value, but also with the new node potentials pi prime, I still fulfill the complementary slackness conditions. And this I show by showing these two statements here. So whenever the flow value is larger than 0, then the new reduced cost coefficient would be non-positive, smaller or equal than 0. And whenever the flow value is smaller than the upper capacity, then the new reduced cost coefficient will be non-negative. That means that whenever it would be strictly positive, the new reduced cost coefficient would be strictly positive, then the flow value must be equal to 0. And whenever the reduced cost coefficient is strictly negative, then the flow value must be equal to the upper capacity. And that is exactly our complementary slackness optimality condition. Okay, so let us see why this is true. So we want to show that these two implications, so whenever the flow, the old flow, is strictly positive, the new reduced cost coefficient is non-positive, and whenever the old flow is strictly below the upper capacity bound, then the new reduced cost coefficient is non-negative. And that is with respect to the new node potentials pi prime, which were obtained by subtracting the shortest path distances or cheapest path distances. So let us look at the first case. So whenever we have a strictly positive flow value, f, that means that the reverse arc will be part of the residual graph by definition of the residual graph. And that means that the distance to get to u is at most the distance to get to v plus the length or cost of that arc. So distance to get to u is at most the distance to get to v plus the length of the corresponding arc, which was the reduced cost coefficient. Now, what implications does this have for the new reduced cost coefficient? So C prime from u to v. Let me just write down what the definition was. So that's the cost from u to v plus the potential difference. So I write it as minus pi prime of u plus pi prime of v. Now let me just plug in the definition of the new reduced costs here. So this is equal to C cost from u to v minus pi of u plus pi of v, and then plus distance to u minus the distance to v. And now if we remember, what can I say about the distance to u minus the distance to v? Well, we had this triangle inequality up here. So d of u minus d of v is at most the reduced cost, the old reduced cost from V to U. So this thing here is at most the old reduced cost from V to U. And what do I have here? Well, this is just the old reduced cost. So this is the reduced cost coefficient with respect to the old potentials from U to V. Okay, but now I know that the reduced cost coefficient from U to V is minus the reduced cost from V to U. Okay, and that implies that this whole thing is at most 0. So smaller or equal than 0, and that's exactly what I wanted to show. The other argument is kind of symmetric. So let's assume that the flow value is below the upper capacity W. So that means that the arc in the direction from U to V is in the residual graph because the arc is not saturated. And that means we will have a triangle inequality in the other direction. So the distance to get to V is at most the distance to get to U plus the length of the arc. And once again, what implications does this have on the new reduced cost? So C prime from U to V, again by definition, that's the cost from U to V minus the potential difference pi prime of U plus pi prime of V. And now let me just shortcut. This is just equal to the old reduced cost from U to V plus the distance difference, so plus d of U minus d of V. And now I can see that if I look into my triangle inequality up here, so d of U minus d of V is at least the old reduced cost from U to V. So that means this thing here is at least, minus the old reduced cost from U to V, which follows by using this triangle inequality up here, and hence this whole thing is indeed larger or equal than 0. And that is what I needed to show. Okay, so we have convinced ourselves that these two implications are correct. When we started with the old flow and the old node potentials fulfilling the complementary slackness condition, and well, these two implications 1 and 2 exactly give me these two implications. So whenever the new reduced cost coefficient is positive, the flow must be equal to 0. Whenever the new reduced cost coefficient is smaller than 0, the flow must be at the upper capacity. And that means that we have, for the given flow F, another node potential pi prime, such that these two are still a complementary slack pair. So we still have an optimal flow, and we have another set of node potentials fulfilling complementary slackness. But this new set of node potentials now has a nice property that with respect to this pi prime, I can now just send flow on top of the given flow F, and I don't have to prove anything anymore. Okay, so the flow augmentation by this flow G0, that is a flow where I only use edges with new reduced cost coefficients equal to 0, right? So that happens only on those edges with 0 reduced costs. And that means that the new flow with a new node potential pi prime still fulfills the complementary slackness conditions just by definition, because we do not change any flow value for these edges. We only change the flow value for the edges where the reduced cost coefficients are equal to 0. Okay, and that finishes the correctness proof already. So finally, a quick word on the computation time of this algorithm. So here we have the corresponding theorem saying that the primal dual algorithm has a computation time which can be upper bounded by this expression here. And what you recognize on the right-hand side, that would be the time that it takes to compute a maximum flow in the residual graph with 0 reduced costs. And that means here we have an upper bound on the number of iterations of the algorithm. So this C, for instance, is just a maximum cost coefficient, and the value is just the value of the flow that we want to send from S to T, right? I think the first statement is clear. So since in each iteration we are sending at least a flow value of 1, after that many iterations, after value many iterations, we will have to be done, right? So that is clear. But why can I claim that I also have an upper bound on the number of iterations of the order n times c? And that comes from the following consideration. We look at the potential of the terminal node t. In the beginning, that potential was equal to 0. And I claim that in each iteration, the potential of the terminal node decreases by at least 1. And this is actually left as an exercise for you, there is a global lower bound on the potential that the terminal node could have, and that is minus n times c. And if it increases in each iteration by at least 1, and there is this global lower bound on it, then after that many iterations, we must be done as well. And therefore, we get this computation time. So why is this true? So in each iteration, the potential of the terminal node decreases by at least 1. This is also easy to see because each time we are sending a maximum flow G0, which is a maximum flow in the network consisting of the edges with 0 reduced costs. So that means in the residual graph, once I have sent this flow, there is no ST path anymore of 0 length. Okay, so all the ST paths that are remaining in the actual complete residual graph will have lengths at least 1 because I'm saturating along all the paths which have length 0. And that means that the distance of the terminal node from the source will be at least 1. All the 0 distance paths had been saturated. So that in the next iteration, the distance to t will be at least 1. And then we just have to remember the update of the node potentials. So the potential of the new potential of t is just the old potential minus the distance, and this distance is at least 1. And therefore, this node potential decreases in each iteration by at least 1. And of course, each iteration is actually dominated by this maximum flow computation. We have to compute shortest path lengths once, that would be Dijkstra's algorithm, and we have to compute a maximum flow, and that maximum flow computation really dominates each of the iterations. Therefore, we obtain this upper bound on the computation time. Notice that this is not a polynomial computation time in the size of the graph because it really depends on the values. But nevertheless, the algorithm in practice is very fast. All right. So that finishes the analysis of this algorithm, and let me finish the lecture by a little outlook on what we are doing in the next lecture, because as a side remark, we have obtained the following. So remember the formulation of the minimum cost flow problem as a linear program here, and that would be the corresponding dual linear program here. And what we have shown by this primal dual algorithm, that we actually computed an optimal solution to the primal and to the dual. And this optimum solution will only have integer values, okay, so integer variables. That is because in each iteration we are sending a max flow, all the input data is integer, and so the flow augmentations and also the updates of the dual variables pi, that only happens in integer amounts. So we will have computed by this primal dual algorithm integer optimal solutions to these linear programming problems. And at the outset, the existence of optimal solutions, integer optimal solutions, is not even clear, right? It could be in principle the case that I would have to send fractional amounts of flows along the network in order to obtain a minimum cost flow, right? So the next lecture is going to be about, say, the mathematical structure or the mathematical reason behind the fact that for these linear programming problems, we can always compute integer optimal solutions, even though in the formulation of the problem, this is not strictly required, right? And that is going to lead us to the notion of total unimodularity. So that is the topic of the next lecture. Under what conditions can we expect integer optimal solutions to general linear programs. So I thank you for your attention and see you for lecture number 8.